Good morning, everybody. Come on in if you're interested in our Building Energy Modeling CEU session. My name is John Rath. I'm Director of Operations for NY-GEO. I serve at the will of the board and Christine Hoffer, and it is good to see you folks here. Glad we can get this CEU session design track launched. I assume some of you are here, many of you for the credits. Raise your hand if you've registered for the credits. Okay, is there anybody here that hasn't registered for the credits specifically? Wow, okay, good to know. For you folks, if you're gonna get the credits, you must, before you leave here, go back to the NY-GEO website registration and register for the credits. We can't do anything unless you register for it. That's the first thing you've got to do. The second thing you've got to do is I'm going to be at the back of the room at the end of the session. I have to have your signature. So if you register and I don't have your signature, the New York State Society of Professional Engineers, you're not going to do anything. We got to have both. For those of you that have registered, all I need is your signature. Make sense? So everybody's got to sign. And those that have to register, register. I would like to thank Con Ed. I don't know if there's a Con Ed representative in this room, but for being a presenting sponsor for us, thank you very much. Today I have the pleasure of introducing our first speaker, Jaclyn Kinson, who is the Climate Resilience Discipline Leader for MEP and Energy at CDM Smith. Jackie is a mechanical engineer. She has been working now after graduation for 6 years. She is in the exciting world of U-10s, and that's what she's here to talk to us today about. I have to compliment her because, and it's definitely a compliment, not an insult. It's nice to see the generation of the future that's going to be riding this huge wave of geothermal energy industry growth. So Jackie, this is exciting for me just to have you here. Jackie has a BS in chemical engineering, and with that, I'm going to ask her just to begin the presentation. We will have questions and answers at the end, Jackie, or do you want to take them during?
Either one works for me. If you have questions, feel free.
Okay, we've got a small crowd, so we can answer, we'll take some questions during the session. Please help me welcome Jaclyn Kinson.
Good morning, everyone. Thank you for the warm welcome. I will be speaking today about building energy modeling and how it's the foundation of a geothermal heat exchanger design. So the learning objectives today are to understand the components of the building energy modeling, to understand the effect of building energy modeling of a ground heat exchanger designed for an individual building, and then the third is to understand it for a district geothermal system. So building energy modeling is used to determine heating and cooling loads to size your equipment, but it's also used to simulate the energy consumption of the building, which we use in energy efficiency, code compliance, and also designing a ground heat exchanger. So with these building energy models, we create 8760 data, which is used to get an hourly load of every hour of the year for your building, and then we input those loads into the ground heat exchanger design. So some of the building energy modeling tools that are available are manufacturer-based from Train. They have their Trace 3D program. Carrier also has an hourly analysis or HAP program that we use. eQuest is the DOE2 energy modeling software, which is used in LEED certification and code compliance requirements from ASHRAE 90.1. And then there's also Energy Plus, which is DOE's open source whole building energy modeling software. And there's also many more. Some people have preferences. You just have to be wary if there are any requirements for your project where it's located or any standards to know which one to use. So some of the building energy modeling components that go into your building energy modeling. First is the weather data. So based off of where your building is located to the closest weather station, you'll pull a TMY weather file, which stands for the typical meteorological year. This is a representative weather and climate data file, which is over a 1-year period and is statistically derived from the past 10 to 30 years of actual meteorological data. And so the most recent one right now is TMY3, and that's from the years 1991 to 2005, which kind of begs the question, is that really representative of the weather going forward? But that's a completely different conversation to have. The next one is your building area, the square footage. So depending on how big your building is, that's really going to drive the heating and cooling loads. Also, the building occupancy is going to drive your temperature set points. So if it's like an occupied residential space, it'll be anywhere from like 70 to 75 degrees. Typically, if it's an unoccupied mechanical space, it may be, your heating set point might be more around 50 to 55 degrees. And then the building occupancy also determines when the heating and cooling is required. When do you have people in the building? Is it a residential building where people are typically home in the morning and the evenings? Now with work from home, are they there all day? And then also in an office building, are they typically there maybe on a more 9 to 5 basis? And when are those loads happening that you're going to need the heating and cooling? Ventilation air, ASHRAE 60.2 specifies these requirements. So we need to bring in outdoor air into the space, which is unconditioned, and then you need to condition it to maintain your space temperature, which adds to your heating or cooling loads. There's also internal loads of maybe electrical equipment that's in this space, your lighting, when your people are in the building, radiating heat into the space, which could decrease your heating loads or increase your cooling loads. Then we also have the building envelope, which helps mitigate the heat transfer between the ambient outdoor temperature and your indoor temperature of the space. And the U factor of the windows, walls, roof can help reduce that heat transfer. And so there's code minimums through the International Building Code and also ASHRAE 90.1. And then there's also more stringent and efficient standards such as the passive house design. Then we also have infiltration loads, which are when unconditioned air leakage comes into the building, which can affect your building load significantly. And then already touched upon this a little bit, but it's really understanding your building schedules and when you're going to have people in the building, when your lights are going to be on, so you can understand those, when those internal loads are really contributing to the heating and cooling loads. And so not every project is going to be a nice new greenfield, new construction project. Sometimes existing buildings will be looking to convert to geothermal, and so you need to really understand what their loads look like based off of site visits, existing plans, and you can start to build your energy modeling. Some existing buildings will have poor insulation or no energy efficiency measures yet, which will lead to higher building energy loads if those aren't already integrated into your project. For new projects that are built to code compliance or ASHRAE 90.1, it's important that we include the energy efficiency measures into our energy modeling. And this can include better insulation, BMS controls, or energy recovery to take advantage of any waste heat leaving in your exhaust streams. Then, if you're building your building to exceed code compliance, like the passive house design, as soon as you put energy efficiency into your buildings, you can get heating dominant loads, could become now cooling dominant loads. Like if you have a high-rise residential building and you have good energy efficiency measures, instead of it being a typical residential heating dominant, now you're going to have it become more of a cooling dominant load. So then it's also important to reflect on how the building is actually performing and what heating and cooling loads will be required from your ground heat exchanger throughout the year. So our goal is to capture that actual energy performance versus what we might think it is performing. So we want to ask the question of how are spaces actually maintained? So we know that the design point with the codes is sometimes 72 degrees cooling and 70 degrees heating for a occupied like residential space. But on a hot day, I'm gonna crank my AC down to 68 so I'm not sweating in my apartment. In the winter, maybe I'm a little bit more frugal and I like to wear a sweater and slippers in my apartment, and then I'll keep it to like 65 or 68 so I don't have to pay a high natural gas or electricity bill. Or maybe I'm the opposite and I run really cold and I'm just gonna crank it up to 80 degrees so I don't have to be cold ever. To help with this, we can look at utility bills for existing buildings. This is something you definitely need permission for, and depending on the relationship with the utility, it could be an easy ask or a little bit more complicated ask. But we can use those natural gas and electricity bills to calibrate the energy model and then be able to tailor our modeling so it's a little bit more representative of what's actually happening in the building. So it's important that we understand the complexities of the building operations. So typical schedules are available through ASHRAE like 90.1, but like I said, it's important to tailor it to the specific building. Maybe you have a building that doesn't fit your standard residential home profile and you know that they work from home, so you're gonna have more of that heating cooling load throughout the day. And it wouldn't be exactly like that standard schedule that is provided. It's also important to understand the domestic hot water load profiles if you're going to include that in the geothermal project, especially with us being in the Northeast. A heating dominant climate, it could compound our heating imbalance. So this is something that we've recently been looking into, is how to create those domestic hot water hourly load profiles. So there are some tables available. This is from the ASHRAE HVAC Applications Handbook, Chapter 51 for service water heating. You can see in this top left that is the average hourly hot water use for a residential customer. And so it gives us maybe a peak at about 10 a.m. Sorry, it's kind of small. Hopefully you can see that. I don't know if I have a, I don't think I can make that work. It peaks at about 6 gallons at 10 a.m. But if you look at the next chart on the right, it's for the 95% confidence interval, and you can see that at about the same time, 2 hours earlier at 8, it actually peaks at about 11 gallons. Then there's also the option down below in the bottom left. It gives you the patterns for low users and also high users. So those low users are in the dark black bars. You can see there's only a peak of 2 gallons around 10 o'clock, but then a high user might have a peak of about 9 gallons, both in the morning and in the evening. And then the last graph on the right is just showing you could have a user that peaks in the morning, or you can have a user that peaks in the evening. So it's really important to understand your loads of your building and which of these scenarios might apply to properly simulate the building energy loads that you're going to include in your modeling. They also have some domestic hot water load profiles for other buildings, including dormitories, motels, food service, office buildings, schools, and nursing homes. And so they give it as a GPH per student or GPH per meal, so you can tailor it to the size of the building. Similarly, with the other one, they give 3 scenarios where you could have the average hourly load. You could have hourly loads from the day in which the peak hourly occurred, or you could have hourly loads from the day in which the max daily usage occurred. So if you know that your building may be on the higher end, you can use one of those peak values instead of more of the average value. That would be more holistic of all buildings. So we will pause here for a knowledge check so you can earn those PDHs. So my question back to you is, after listening to me talk about those, what are some of the components of building energy modeling? Sorry, you're gonna have to speak up a little. Schedules? Ventilation? Weather data? Building envelopes? Square footage? There's one more? Space temperature set points, right? That was most of them, great job. So just to recap, we had weather data, building occupancy, building area square footage, the ventilation loads, internal loads, building envelope, infiltration loads, schedules, and space temperature set points. Great job, you've passed so far. So next we'll go into a little bit of how the building energy modeling that we just described goes into the ground heat exchanger design. So they're not just used, like I said, to size equipment, but those hourly loads are inputted into our modeling softwares as a basis for the ground heat exchanger design. So once I'm a mechanical engineer, once we've completed the energy modeling and reviewed the model to make sure that everything makes sense, we work with our geotech engineers to run the GLD modeling, which is the ground loop design modeling, to size and confirm the operation of the ground heat exchanger. Sure. Can you repeat that? Who validates the software? That's a good question. I know we purchase licenses through the modeling software program. Are you asking who regulates that software or who regulates us using it? There's definitely, for building energy modeling, there's different requirements, like I said, based on the projects that you're doing. If you're going for certain certifications, you have to use a certain building energy modeling software. If you're talking about the ground loop design software, I'm not sure who regulates that, but I can get back to you or point you to someone probably in this room who can answer that question. Any other questions before we move on? All right. Okay, so when we use GLD, it looks at every hour of the building energy modeling loads, but it also gives us the monthly and annual totals and the peak hourly load for each month. So the peak loads are important, but the annual energy loads drive that size of the bore field and the amount of thermal drift over time. So up here, you can see that we have 3 different GLD runs for 3 different buildings with different load profiles. So on the far left, we have one building that if you're just looking at the peak loads, there's a cooling peak load in these blue columns of 1,000 kBTUs per hour in July. And then looking at the heating load, it's somewhat similar with 1,400 kBTUs in December. So just looking at those, I would think, okay, maybe we have a good shot at being a balanced system. But then if you look down at the total, this is our total annual load in kBTUs. We have only 630,000 kBTUs of cooling annually, and then we have over 2 million kBTUs of heating annually. So we have more than 3 times our heating load than our cooling load, which is significantly imbalanced. Then if you move to the middle graphic, we have better peaks. So in the cooling in July, we have a peak of 441 kBTUs per hour. In heating, we have 434 kBTUs per hour in December. I'm thinking, okay, great, this is balanced. Look at these peak loads, they're almost equal. You couldn't ask for anything better. But then when you look at your annual loads, we have 500,000 kBTUs of cooling over the year, and then we have about 750,000 kBTUs of heating over the year. So there's still about 1.5 times greater, and so there's still a pretty significant heating imbalance. Whereas when we look at the third graphic, it looks like we have a peak cooling load of 1,200 kBTUs per hour in July, and then we have a peak heating of about 1,100 kBTUs in heating. So just looking at these peak loads, I would say, oh, I guess we're probably going to have a cooling dominant because our peak cooling load is a little bit larger than our heating, but maybe it's somewhat balanced. And if you look at the annual loads, we actually have 1,000,000, about 300,000 kBTUs for cooling, but we actually have more heating load annually and have 1,000,000, about 700,000 kBTUs for the heating annual load. So just kind of looking at these three scenarios to stress the importance of your peak loads can kind of tell you something. They're helpful for designing your loads and making sure your equipment can serve those peak loads in the building. But you also need to consider for your ground thermal heat exchanger design what those balances are annually, and they might not line up with what your peak loads are telling you. So when you have those thermal imbalances, you're going to have a thermal drift in the ground. So on the left, we can see for a heating dominant building, we have our average entering water temperature decreasing over 20 years, or you can see it's 240 months on the bottom. And so this is happening because we have more heating load in our building, so we're taking more heat from the ground than we're putting back into the ground in the cooling season. So we're going to eventually keep making the ground colder, and we're going to have a lower entering water temperature as we go throughout the years. On the right, you can see this is now showing the minimum entering water temperature in that purple color, and then also the maximum entering water temperature instead of the average. Just wanted to clarify that in here. But this is for a cooling dominant system where you see that trending upwards, and we have more cooling load than we have heating load, so we're depositing or rejecting more heat into the ground than we are taking it out to heat during the winter season. Question?
Yeah, can you predict when you'll lose the ground when the drift falls too far out of whack? Like when water temperature gets too cold or too hot, can you say, all right, 10 years before it's not going to work anymore?
Yep.
Yeah, can you please repeat the question?
Yes. So the question was, can we be able to predict when the ground heat exchanger won't be able to provide the entering water temperature? And so that's what this graph kind of shows us. We can see what the entering water temperatures are, and we have our design points. So typically it could be anywhere from like 40 to 80 degrees or 30 to 90 degrees. And as long as those lines are within those two temperatures that we're looking for, like you can see on the right that they just make it to 90 degrees at the 20-year mark. But when we're designing, we want to make sure that we have enough boreholes and that it'll last for those 20 years. But if we're seeing like significant thermal drift, if we have too little boreholes or something like that, and those entering water temperatures exceeds those like design threshold points, then we can say, okay, it won't be able to serve us past X amount of years. Oh boy, here we go. Question for you back there? Yeah, so the question is, why is our temperature range like 30 to 90 degrees, whereas in Europe we're seeing, I think, 25 to 100? 110, thank you. I think it's mostly because we are designing for the heat pump efficiencies that we're seeing in the equipment. And then I'm not sure if it's trying to like go through the GLD iterations. It's mostly for those heat pumps and the efficiencies that we're seeing at really, really low temperatures or really, really high temperatures. Yep, yeah, and that's a good point. So just to repeat what he just said, those peaks are at like, could be a small amount of time that you would see 90 degrees or 30 degrees entering your heat exchanger, or sorry, your heat pump. So then you can evaluate at those times when you're getting more of a range in between and those higher COPs instead of how much time it would actually have that lower efficiency. So definitely something to consider. Sure.
Hi, so do we expect that to flatten, or will it continue to pull? Obviously, ground temp is gonna have it flatten, but do we expect that to fail at some point, or is it gonna level out? What do we expect for a design?
So it won't level out. It will continue to drift. As you add more cooling load in, the ground will continue to get longer. It'll continue to get hotter. And then opposite, for if you have a heating dominant, the ground will continue to get colder. We're just looking at a 20-year snapshot right here.
Jackie, you know where you are in the presentation. Do you want to take more questions now? Should we hold them?
I might continue because I think maybe going through some of the optimization of the ground heat source design will answer maybe something that's stirring in your head.
Okay, great.
Okay, so like we've been stressing, the energy loads are the most important aspect of the ground heat exchanger design. What my geotech engineer was saying was that if you have garbage energy loads in, you're gonna have garbage GLD results out. So you really wanna make sure that your energy loads are representative of what's happening in the building, and you're taking into account all the energy efficiency measures and things like that. We were actually looking at a situation where there was extremely imbalanced loads. We were kind of just playing around at this point, and we weren't getting results even if we put in like an obnoxious amount of boreholes for just an individual building because the imbalance of the loads were so high. So what we can do is really look at those annual loads because they dominate the thermal drift, but there are some small changes that we can do in the optimization of the ground heat exchanger to mitigate that drift. So if we look at this example, we have a residential building that's heating dominant, so we're seeing that thermal drift of the ground cooling off. And we can see that there was a peak of 399 kBTUs per hour for cooling, and then we had a higher peak of 531 kBTUs per hour in January. Looking at those annual loads at the bottom there, we have about 500,000 kBTUs of cooling, and then about 1,850,000 of kBTUs for heating over the year. So that's why we see that heating dominant thermal drift. So we ran with GLD, and these are the results we got with 22 500-foot boreholes spaced out 30 feet on center. And so then we reran it, knowing that we had some space constraints on the site, and we reduced down to 11 boreholes, and then we increased that length to 800 feet, keeping that 30 foot on center. And so with those couple of parameters, keeping the spacing the same, and then changing the number of bores and about the 800, or increasing the depth to 800, we saw a similar drift. Nothing really changed. We see the same pattern. It's maybe a little bit flatter, but you can see we have those same loads on the left, and then we still see that thermal drift, and it's maybe a little bit flatter. So, and these are just the two connecting them, and it's just, we didn't change anything with our annual energy loads, so it really shows that it's important to make smart building decisions and capture those design decisions in the energy modeling. Because even though you can make small changes to mitigate the bore field, it's not going to be able to solve all of your load imbalance issues. So then we'll go through another example of an individual building. This is for some of you who may have gone on the tour yesterday for One Java in Brooklyn, New York. It's a mixed-use new construction building with 800 residential units, over 13,000 square footage of retail, and below-grade parking. And of those 800 residential units, 30% are for affordable housing. So in the loads on the right, you can see that we're now a cooling dominant for, even though it's a residential, it had some of those energy efficiency measures in there. So now it's become more of a cooling dominant building with about 1,300,000 kBTUs compared to, 13 million kBTUs compared to about 9 million kBTUs for heating. So we installed 320 boreholes, 500 feet deep at 15 feet on center. The building is being served by ground source heat pumps in each of the apartments and common spaces. There's electric heat in the mechanical rooms and storage rooms. And then because of this thermal imbalance, we maximized the number of bores that we were able to put in the ground, and then we needed a dry cooler or the supplemental equipment for that long-term thermal balance and performance. So we were able to reject some of the heat during the cooling from the system, and we wouldn't have too much of a thermal drift in our bore field. So another knowledge check. How does building energy modeling affect ground heat source design for an individual building? I stumped you. Size of the bore field? Yep, number of boreholes in your bore field. Yep, determining the thermal drift from your annual loads. Then I had one more that I snuck in there. You can use supplemental heating equipment, so you can, or cooling equipment. So you can have like an electric boiler on your system if you need to add heat to address that thermal drift. Or you can have a dry cooler or some other form of like an air source heat pump chiller, so you can reject that heat from the system if you need to. I'll pause here for any questions that might have been lingering during that, or were some answered?
Oh, I'm sorry.
So, as this thermal drift happens, can you describe the efficiency of the heat pump as that thermal drift occurs? And is there some critical point in which the thermal drift makes it so air source heat pumps are more efficient given the same building envelope and other parameters?
Yeah, so we really designed to maintain those entering water temperatures. So kind of again, if you have so much of an imbalance and you don't have enough space for your boreholes and you exceed that entering water temperature, then you'll start to see declining efficiency. I can't tell you exactly what that efficiency is compared to the air source heat pumps, but that's when you do start considering, okay, maybe I need a hybrid system, and my bore field's not going to be able to maintain it all.
You
Over
tell
there.
me.
Okay, over there I saw.
You get to choose.
Yeah. What kind of data are you exactly looking for from the geotechnical engineer?
That's a good question. So they look at like soil conductivity, thermal conductivity from like a test borehole that was taken, and then there might be some others that I would have to ask and get back to you on. Those are the ones that are coming to mind. I think we had a question right down here.
The modeling, sorry, thank you. Is there a reason why the modeling stops at a 20-year projection? I mean, you have this system in the ground for hopefully a very long time, and it needs to perform over, let's say, 100 years or more. What's the limitation there?
Yeah, I think it might go hand in hand with some of the equipment lifetimes that we could see are like 20 to 25 years. I'm not sure if I know the exact reasoning behind the 20, if there's like a certain standard or things like that. It's just what we've been using. I can get back to you on that one though. I saw right there.
Thank you. So Sylvie Livescu with Bedrock Energy. So thermal drift. If you go back to your plots about losing 5 degrees over 20 years. Yeah, the previous one. You showed 2 scenarios with 22 boreholes, 500 feet each, and 11 boreholes, 800 feet each, right? So in the first scenario, it's what, 11,000 feet?
Yeah, 22,000 linear feet if you do like.
In the second one, it's
Yep.
actually less.
Yeah, 17,600.
So just looking at the length, I think it's not enough. I think you have to take into account the thermal conductivity, the downhole temperature, so all the physics involved.
Yep, yeah, there's a lot of other like configurations of the boreholes,
Right,
things like that.
and when we talk about drift, think about it as an energy system in which you put energy in and you take energy out.
Mm-hmm.
If you put more energy in, eventually you lose energy, right? So your drift will increase. So what you need to solve for is actually enough linear length of boreholes to make sure that your drift is kind of leveled over 20 years or whatever interval you need.
Yeah, so I pointed out just the different number of boreholes and then the different lengths, but there are other things, kind of like you're saying, like the configuration, how much empty space you have around versus like boreholes close together that could be implementing the heat transfer like between the ground and the borehole. And there's like other things that go into it, not just the number of boreholes and the length, yeah.
Have you looked? Do you have any data to show how
Not in
important
this
both are?
presentation, yeah.
All right.
Trust me, I was trying to figure out like everything that goes through our mind, try and put it in here, but there are some things that were missed.
All right, thank you.
You're welcome. I think we'll go down here and then go back.
Thank you. Actually, I just have a comment. I can feel Dr. Kavanaugh channeling through me, so I just need to make a few comments here. You have to remember that this is a model. This helps you get to the right answer. There needs to be some engineering judgment. Keep in mind this is TMY3 data that is, with the climate change, we're seeing that some deviation, at least where I'm practicing engineering. You have to remember this is taking into account the EER and COP of the equipment over a range of temperatures. The thermal properties that you get when you do a thermal properties test, that information is within 10% accuracy of what's really going on. And one thing that this model doesn't take into account is the moisture in the soil. And so if you have a cooling dominated geology, some of that heat of vaporization is going to help you so that you don't see the drift that is predicted with some of these models. So I would just caution you to look at the data, see what's actually happening with real installations. With any kind of simulation or modeling, you need to field verify. So I think as an industry, we need to do more of that to try to help us get to the right answer.
Thank you. And then we will do right
You had
there.
your hand up. Sorry, folks.
You showed several different load software packages, and some of them, like Train Trace and Carrier, exclude internal loads from the heating side, but eQuest includes those. How do you handle internal loads in this when you input it into your loop design? Do you always include them on the heating side as your inputs?
So internal loads as like people in the spaces and
Yes.
the equipment, yep. Those are actually included in the Carrier Hourly Analysis Program and Train Trace 3D as well.
Okay, so they're always there when you design your bore field.
Yes.
Okay, thank you.
Project we have for this in Brooklyn, one Java Brooklyn, you have 320 boreholes. I don't know what the dia is. On the other side, building in one of your model, you have 18,000 boreholes. So I think the number of boreholes depends upon the size of the project. However, what's the depth of each borehole is, and what's the diameter of each borehole is, and is the offset, like in this case, 15 feet? On the other case you just showed in one example, the off-center is 30 feet. How did you decide what's the diameter is and how deep is in the ground those boreholes is? Maybe the software does, I don't know. See if you can shed some light on that.
Yeah, those are design decisions that we make in the project based off of available land space. Maybe you have a really small site and you're really constrained to the number of boreholes that you can have, so you might have larger flow, so a larger diameter through, and you'll also have a longer bore field depth. But if you have a little bit more space, you can have shorter boreholes, and then you can have a larger number of boreholes. So those are all things that we kind of do like iterations through in the ground loop design, so we can understand how it's working, and then we can optimize based off of some of the project constraints. And we do have like typical design points that we would design around. So we have ranges of like flow rates through the boreholes, we have spacing. You can see they'll differentiate between different projects depending on how much space we have. And then that also kind of comes into play with the diameter as well, with how much flow we're trying to get through.
Jackie, again, you know your presentation. Do we have time for more questions, or you want to move forward?
I'm gonna hit the last couple slides just so we can talk about the district geothermal systems, and then we should have some time for some questions at the end too. Okay, so for the district geothermal systems, we kind of have this potential or flexibility to balance the heating and dominant or cooling dominant buildings within that entire system, because we're working with a group of buildings instead of just an individual building. So I've been working on a lot of the U10 and network geothermal projects, and commonly they'll look first, where do we locate this project? And so they'll evaluate around 20 or more sites and then eventually get down to one. But we kind of, at this feasibility level, we have to decide, where do we begin and how much effort do we actually want to do to put into the accurate building energy modeling if we're looking at multiple sites. So we've used data sources like the public assessor's information, so then that we can apply EUI factors based off of the occupancy of the building and the square footage of the building to get an idea of what those loads are. So then once we've selected a site, we can go into that detailed design phase and perform like manual J calculations for a single family residential home, or we can look at existing plans and perform site visits so we can build out those detailed energy models. Once that site is selected, and we can spend some more time on really looking into getting that energy modeling accurately done. And so once we've determined, and while we're determining who's going to be connected to that network system, we really want to keep in mind that we want a diversity of loads. So we want some commercial, we want some residential, we want some of those heating dominant, and we want some of those cooling dominant buildings, so we can create an overall balance in our annual loads. So I'll talk about kind of what we did for the Eversource geothermal pilot out in Framingham, Massachusetts. So this is a network geothermal system constructed and partially operating right now. There's one main bore field you can see up in the upper left-hand side in the parking lot of a community college. And then we have two recharge bore fields throughout the network, one at a fire station and one at a housing authority parking lot as well. It's located in a primarily environmental justice community. We have a mixed loads for system balancing. We have some residential buildings down at the bottom in yellow. Those blue buildings are the multifamily apartments with the housing authority. That orange up in the top left is the community college, and then the pink loads to the right are the commercial loads that we were able to tie in. And so there's about over a mile of ambient loop piping on this site, and we worked with 6 outside stakeholders to integrate them into this project. So looking at that loop, it seems intuitive, like, oh, I'll just draw a box and then we'll connect everyone around it. But we really started out with question marks throughout the site, and it was a mix of outreach of who would be interested in joining the project, along with trying to figure out which of those building loads would be able to be connected and give us that balance. So then we began to build our district system, and so on the far left, you can see that we started out with a 2-pipe system. We had located the community college as that anchor customer, and we were putting one big bore field up in their parking lot, and then kind of spidering out and getting some of those residential buildings to the left, picking up the elementary school, and then picking up those apartments. But then due to expandability in the future and some construction costs, we moved to a 1-pipe system and located a recharge bore field in the apartment buildings, and we're connecting some of the same residential customers, but starting to shift over a little bit. Then as we started to really analyze our loads and who is being connected, we needed to find some more commercial customers to really balance out the loads. So we went over a couple of streets, and you can see our final loop. We have the commercial loads on the right, and along with those residential loads at the bottom, picking up the multifamily apartments and then the community college up at the top. and we were able to locate another recharge bore field in the fire station. And so as we were finalizing who is connected, we really took a close look at those building energy loads, put together the hourly load data for each building, and then we're able to finalize the number of boreholes required at each of those bore fields using GLD. And then we were able to input that into Transys to be able to assess the performance of the thermal system. So like I said, we use those annual hourly loads for each building and inputted those into Transys, which was able to model our ambient loop, the bore fields, and the building connections and what kind of like heat pump they were using. So we use this to ensure that all customers along the loop would be able to receive a similar entering water temperature to provide adequate heating and cooling with similar efficiencies to their neighbors. So we didn't want this to be one big loop where someone further down the line was getting much lower entering water temperature than someone right next to the bore field, and then their heat pump would be operating at a different efficiency and they'd have not equal electricity bills to run the same piece of equipment. And so this graph on the right is showing the temperature distribution at the coldest hour within the loop, so we can see if we start at the 20 borehole ground heat exchanger number 3, we can see that it kind of decreases along the line, and that's when each customer that's taking water or the fluid with propylene glycol from the ambient loop, running it through their heat exchanger, which will then go to their heat pump and then come back into the loop, returning with slightly lower temperature. And so you can see as each customer is connected, we get slowly lower and lower temperatures from about 42.5 down to just below 40 degrees, where we have a recharge bore field where we're able to take heat from the ground to boost our entering water temperature. And then the process repeats with the customers along that next line. Temperature starts to decrease. You can see there's a sharper decline if we have a larger load customer on board, and then it increases even more when it reaches our main bore field, and we go up to about 44 degrees for the entering water temperature. And so we'll do one last knowledge check, and I think we'll have some time for some questions, but after going through that, how does building energy modeling affect ground heat exchanger design for district buildings instead of one individual building? Say that again? Yep, balancing the heating and cooling loads. That was really the main one on that one, because you have multiple buildings to choose from versus what you're stuck with for one individual building. So with that, just go over what you learned today. You now understand the components of building energy modeling, and you now understand the effect of building energy modeling for both individual buildings and district of buildings for your ground heat exchanger design. So with that, we have about 10 more minutes for questions.
Try to get some folks that haven't hit.
Yeah.
Thank you. Just a question about the building energy modeling. Do you have case studies where you've checked the models you've built versus real building data? Like to date, I'd like to check the validity of your energy models.
Yeah, so we've used those utility bills to be able to tell what they've been using for natural gas and electricity, and if you know the efficiency of like the existing equipment in there, we're able to use those to calibrate our energy models and make sure we're accurate. Yeah, then we'll go around this way.
Question. What are some of the limitations that you found using GLD as I guess your software of choice? And overall, I guess how do we start working around some of these limitations that we find with all of these modeling softwares? Because it seems apparent that they're not there yet in terms of fully exploring all of the particulars that we need in going into ground source projects. So I was hoping you could talk a little bit about that.
Sure. I think what Lisa said earlier, it's good to think critically when you're using these modeling systems, to really think about the parameters that are going into it and what that does to your design, not just looking at the results and being like, okay, this is it. Really thinking critically about what you're putting in and maybe those effects are. You'll see in the district system, We used GLD in combination with Transys because we were able to look at the performance of the entire system rather than just looking at the bore field on their own. So I think it might even be like a combination of different modeling softwares as well.
Jackie, we've got a request to go back to the previous slide if you can.
Sure. This one? I think over here.
Yeah, back to the thermal drift. I'm just trying to wrap my head around it. So if there's a system that essentially will be not as useful in 20 years, is there like a recharge period? Like if you move to another field nearby, that in 10 years you could come back and reuse this system? Or is it kind of a one and done and we have to move on so many linear feet away? Is there a recharge?
Yeah, I don't think it would be like in an instance where you would let it be and then come back to it. I'm not sure if we've, like as an industry, looked into that, of like abandoning a system, leaving it, and then coming back to it. But I think you would try to just avoid the thermal drift and design to mitigate it, whether that's number of boreholes or like your configuration, or using supplemental equipment to mitigate that drift instead of just leaving it to offshoot.
Can you speak a little bit more about what kind of modeling, if any, is done on the distribution system of this thermal fluid throughout the district? You know, flow rate, pressure, what kind of water or fluid cavitation is occurring in the loop in general? Thank you.
Yeah, so we did not only the thermal distribution in modeling with Transys, but we did also have a separate hydraulic modeling. I'm not exactly sure what like program they used or anything. That was someone else on our team who actually did that effort. But we did go through the motions to make sure that it hydraulically worked and did that model along with the thermal modeling. I think we, oh, right here.
Thank you, excellent actually, of course. What's the tolerances you have for the temperature drift? Like what is acceptable temperature drift over 20-25 years? I do understand we're all targeting the stable, but there is supposed to be some kind of range, correct? What is the industry accepted range, at least in US?
I don't know if I would be the one to put that standard out there. I think that'll be a collective effort of how much drift we would allow. It's really driving those entering water temperatures of if we exceed what we want for the equipment, that's when we would say this would be too much drift. Correct. So the question was, as long as you were in the minimum and maximum entering water temperature, it would be okay for that system. I think we have one over here and then one over there. Oh, never mind.
For the geothermal system you showed, was that the modeling or was that the actual temperatures of the loops on that coldest day?
This one? Hold on.
Yes,
This
that
one?
one.
This was the temperature in that ambient loop on the coldest hour. So we're looking at just that, just the coldest hour when it's at these like 40-degree temperatures, but it'll fluctuate throughout the year.
Is that modeled or
Yes,
the actual temperatures?
this is modeled.
Okay. Did you guys collect the actual temperatures?
I think that's in progress. So
Okay.
there's like a verification program happening right now, M&V, that they're doing to track the pilot project to see how it's operating.
So next conference.
Maybe. Might not be me. I think we'll go around here, and there was another question over here.
Back to the start of the presentation when you're comparing three scenarios, right?
Mm-hmm.
And you were essentially balancing the loads. What was the difference between each scenario? Like, how did you change it so much?
They were different buildings. I don't know exactly like what the parameters were for each building, like size or occupation, but they were just like 3 different ones over the years that we've been able to, that I just pulled as good examples.
Right.
I think question back there at the table.
Thank you. Sorry, I'm not an expert in this stuff by any means, but so the graph with the drift, you're designing, or there's an acceptable drift for a type of heat pump? Is that what your type of geothermal pump? Is that what you're saying? An acceptable range of drift for a type of heat pump? So in 20 to 25 years, when that drift is getting worse, would it potentially just not be an issue if you can just replace the heat pump with a much better heat pump?
Yeah, that's a good point. Like, as technology gets better, we'll probably have heat pumps that can operate at lower or higher temperatures, and your efficiencies will be better. So that is, going down the line, probably a good solution.
Thanks.
Jackie, I'm looking at the clock. We probably have one more
Sounds
question,
good.
and then, folks, Jackie's not going anywhere, so you got plenty of opportunity to talk with her, and I'm going to reiterate what we need to do for credits. So you get to pick. I don't want to be the bad guy.
We'll go in the far back.
Okay.
Hi, mine is just a quick question. What brand manufacturer of heat pumps have you been using or looking into?
We've looked at a lot of them, so I think depends on different projects, but we've used Climate Master, we've used Train, we used Water Furnace, we've used Samsung units. We look at like all of them.
Okay, cool.
Okay, ladies and gentlemen, first of all, how about a round of applause for our presenter?